Hello and welcome back. We now take a closer look at the technical side of storing data and talk about data storage systems. So before we start, we need to be clear about what do we need to store. We typically have a combination of different data types that we need to think about. For example, we may have measurements like timestamp, sensor ID and a value. We may have unstructured data, anything that is text or images, some types of scientific data. We also may have structured data, anything that can be represented in row and columns, like think Microsoft Excel. And we have a lot of software. For example, we have software environments, we have the software themselves, we may have machine learning models, information about how we train these, and so on. So let's start with the one you're probably most familiar with a file system. We have different file systems on different operating systems, like for example we have on Windows NTFS, FAT, EFS and so on. On Apple we have an Apple file system. On Linux we have a choice of different file systems. Typically we use X3 or 4 these days. So what does a file system allow us to do? They store the files on our local computer and they sort of add a layer between the hard disk and the user. It allows us to have some hierarchies, and you're most familiar with this in terms of folders and folders within folders and folders within folders within folders and so on. They typically work well on your local computer, and as storage capacities has grown a lot in the recent years, it works well to up to some terabytes and so on. You yourself need to organize how you store the data. You can put everything into one big folder, or you can have more elaborate, detailed system how you create and name folders. One advantage is that it's a very generic approach. It works for all kinds of data, but it's not so great across networks. It's okay sort of on small networks where the computers are connected all the time, like your local institute network, for example. It's not so great with laptops, because laptops often get disconnected or they go to sleep, for example. And it's also not so great for large data that we want to share across networks or clusters. We can also move such a file system into the cloud, of course. They appear as a normal file system of the computer, and then they stream or cache files from the cloud. So the files are downloaded or synchronized as required, and the external cloud storage can be much larger than what you have on your local computer. Examples for these are, for example, Google Drive, Microsoft OneDrive, Apple iCloud and so others, but there are also, of course, open source versions like Nextcloud or Skibo and so on. They are convenient to access the files from multiple devices and sync them, but they are generally not suitable for research data management. If you work on a computer cluster, they have their own file systems. They address specific requirements working on very large clusters, and here again you have many different options and you need to choose according to the specific use case. Well, if you build a cluster, you also need to think about if you want to have a generic file system that is not optimized for specific data, and for all of these file systems you also need to organize this data somehow. So it's good within the cluster, but not so great for interacting with the data outside the cluster. And if you build a cluster, there's a whole more technical world to it that you need to consider. A very different approach to file systems are object stores. So here we treat everything as a single object. So we don't have files as such, or folders or hierarchies, we just have objects. That means we have a very simple interface. We can put a file there, we can get a file back out, we can list everything that's in the object store, and we can delete it, and that's pretty much it. So no directories, no hierarchies. Essentially we have a unique ID for each object, and then the object store just puts the object in essentially a big lake. So what is it for? It's good for data archives. It's good for what we call data lakes, so we throw everything in. It's good for write once, read many times applications, so for example for videos, your photos, music and so on. We want to, for example, store data and serve it to customers. But, as I said, it's not a file system. We don't have hierarchies, we don't have directories, and it doesn't behave in the same way as you would expect it, for example, on your local computer. You also cannot mount it as a file system on your computer, so you can't interact with it directly. Well, you could with a special software, but it's sort of fragile, so it's best not to go this downwards route. Instead, you have a certain API or over HTTP or different protocols. One example of these is, for example, is Amazon S3. A very different approach to storing structured data or semi-structured data are databases. So we have here relational databases or RDBMS. They are strictly for structured data, anything that goes into tables. They have very strong guarantees for data integrity. This is how they were developed. More flexibly, we have NoSQL databases. They are not for structured data. They typically work on documents that are encoded in a JSON format. Or we can have graph databases or key value stores or triple stores if we want to focus on ontologies. We also have a special case for relational databases, the time series databases. They're optimized for time series that we have timestamp value, for example, sensor data. So what are relational databases? That means the data are organized in relations, hence the name. So that means we have different tables, and these tables are interconnected. This data model is fixed, so we have a so-called schema that defines which tables do we have, which columns that correspond to variables do we have, and these columns have a fixed type. And then we connect these tables. This is how these databases allow us to have strong guarantees for data integrity. Of course, on the downside, that may lead to potential performance issues because we need to organize everything in these tables and check all these constraints of data types and relations. It also means databases, relational databases, are only usable for data that can be expressed in tables. How do we interact with these databases? There's a language, computer language called SQL, Structured Query Language, that was devised to interact with these kind of databases. Examples for these databases include Oracle, Microsoft SQL, Amazon RDS, and many others, or in the open source world, PostgreSQL, MySQL, SQLite, and many others. NoSQL databases means not only SQL, they support some SQL features but not all. They focus mainly on storage and retrieval of data that is not in tabular format. Typically they are encoded in JSON documents. This set of databases originate from the need to handle ever-growing data with the shift to web or cloud applications, and we have many different varieties we'll look at in a minute. Which one we want to use again depends on the type of data and the use case, but one characteristic is that there's no fixed schema as in relational databases. So that means, by definition, they cannot offer us the same guarantees on data integrity. We'll talk about the cap versus base theorem later, but it's essentially a trade-off between availability, responsiveness of the system, and data integrity. So here are some examples of NoSQL databases that are very popular at the moment. We have MongoDB, CountDB, HBase, and Neo4j. MongoDB is designed as a scalable database and is based on nested documents that are distributed within a big cluster. The underlying document is JSON, actually it's Bison, and it's essentially layers of key value properties. You see an example here on the right. You have a JSON document that we insert into this database, for example a new location here in Aachen, and we have specific properties. So MongoDB is not really centered around relations. We can make this sort of work, but it's not a data model that works on many documents. We want to have single documents with MongoDB, but not a complex relationship. And then we query this with a Perl-like notation here. CouchDB is another NoSQL database. It's also based on JSON-based documents that can be nested as we are required. There are no ad hoc queries, but we have indexed view, and the advantage of this one is that it scales up and down as required. It can run on your mobile phone, but it can also run on a cluster. One characteristic is that it doesn't delete data ever. It only grows and appends. If you delete data, they are just marked as deleted. Again, you access it via an API, And one key feature is that it allows to locally store data offline, then synchronize with the server later. So here you can, for example, see how you interact with such a database. You have a server somewhere, and then you interact with an HTTP interface with an API. And this looks like this. You have a JSON document, as you can see it on the lower right hand part, where you have keys and values, and then you use the HTTP syntax to interact with the database. If you have a very large data set, then HBase is probably the one you want to look at. If you have, for example, many petabytes of data across thousands of servers. So for most of our application, it's probably not ideal because it doesn't run well on small clusters. But if you have a very large database, then you need to look at this approach. It's modeled after Google's Bigtable, which is proprietary, but they sort of reverse engineered the publications around Bigtable and created this database. Here you can see how it works a bit behind the scenes. We have rows that are uniquely identified by a row key. Those cannot be changed once they are set, and they are only indexing allowed by row keys. So it's a bit like a key in a relational database, but sort of it isn't. And then we have columns and column families that are data grouped within the column families. And everything is stored in a cell, and this is how it's addressed. It's a combination of row key, column family, and so on. So you can see there are many common terms with relational databases and other NoSQL databases, but it's fairly complex. And that originates from the fact that it's really meant for very large data. If you have data that is stored as a graph, you can look at Neo4j. There's a commercial version and a community edition, and this is what we call a graph database. So it focuses on information in nodes and edges and how to retrieve information with relation between those nodes. It's useful for many one-to-many relations. It is something that, for example, traditional relational databases are not very good at, because they can model relationships, but not to the extent that graphs database can. One key point is that they're schemaless, but you have indices and constraints, and again you interact with it either with an API or with their own language. As we mentioned before, a special case are time series databases. So time series are, we have a sequence of data pairs, timestamp and values, like for example measurements, sensor ID, value or temperature, and a timestamp, or stock market, or search engine traffic, and so on. You can see an example here on the right. You have a timestamp going on the x-axis, and on the y-axis you have a temperature measurement. So of course you can store them in relational databases, but as you probably will have large number of these measurements, you can run into performance issues, and hence you can run specific databases that are based on the relational model but dedicated to time series. One aspect to consider is if we have streaming data or not. So we may have a continuous flow of real-time or near real-time information, for example transactions or sensor data, Internet of Things, and so on. We need to make a choice how we process this data, either in batches where we collect data for a given amount of time and then process the accumulated data, or event-driven, so as soon as something happens or new data arrives, we do something with the data. There are many streaming solutions like Apache Kafka, Flink, Storm, Amazon Kinesis, Google Dataflow, Microsoft Azure Stream Analytics, and many more. So again, we need to look at our specific requirements and then make a dedicated technology choice. For example, here in Kafka, we can organize the data in producers and consumers and stream processors, and Kafka is sort of the mediator that collects all the data from the producers, gives it to the consumers, and interacts with the stream processors and storage connection systems. The other storage solutions like Flink and Storm and so on, they have different properties, and again you cannot make a very generic statement. You need to look at the specific setup that you have and then see which advantages and disadvantages each solution have. If you have a lot of data, you will also need to have backup. Typically, we still do this on magnetic tapes, and we have large robots that inserts the correct tape upon request. So we also need to have special access software to read and write the data, and tape libraries have the advantage that they're very good for long-term storage of very large amounts of data. And that is because the magnetic tape is very durable, but it also has a very good cost ratio per amount of data. A typical size per tape is about 20 terabytes, and then you can see here in the background image you have many of those tapes in a big library. They are very slow compared to other options like hard disk or SSD. They're really meant for long-term storage, often also called cold storage. So how do you choose the right tool, or rather the right tools? You will likely need a mix of technologies, so there is no single answer or silver bullet. Here are some questions that you can ask yourself, and then you need to step through the different technology choices and see what's optimal for you. So what kind of data do you have? Is it structured, unstructured? Is it more document, or is it maybe organized in a different way? How much data do you expect? It makes a difference if you have a few terabytes or hundreds of terabytes or a petabyte. Do we have streaming data at all? If not, that makes our lives, of course, a lot easier. If you have streaming data on top of dealing with structured, unstructured graph data and so on, we also need to process the stream of data. How do we handle data and their metadata? How do we describe the data? How do we store the description of the data? How do we want to search for the data? How do we handle data quality issues? But it also, more on the practical side, how do we operate the systems? Do we have which expertise do we actually have, or can we get? What are people familiar with? It also limits our technology choices if we have maybe a set of tools that are great but nobody can use them. We also need to think about where the data comes from, and more on the organizational side, do we have sensitive data like industrial data, non-disclosure agreements, medical data, personal data, and so on. If we do have these kind of restrictions on data, we also need to think about how we can access the data, how we can safeguard the data and implement access control systems. So you can see that building a storage system is not a trivial task. We have many data handling and data storage options, ranging from our local file systems to cloud file systems or a cluster, object store, different types of databases, stream processing, and so on. So one system doesn't fit all our requirements, so we will likely need a mix of technologies. That means before we start building our research data management setup and framework, we need to be clear about our use case and also what do we want to achieve. We need to think about what kind of data do we have and how we can combine probably different tools that we need into one effective systems. And of course, we have an ever-changing set of tools, and what was the optimal choice maybe 5 years ago may be better with a different choice for the future. We need to think about the longevity of our data, as we need to store and process data for more than 10 years.